Hello everybody and welcome back. We're on question B2 from the 2016 Cimc Canadian Intermediate Math Contest. Okay, so B2 starts to be a bit more challenging, and we still have to keep in mind written solutions. So let's take a look here, and hopefully you've tried this one already. If you haven't, please download a copy of the contest, give it a shot before watching any further. In the list of positive integers, 1, 3, 9, 4, 11, the positive differences between each pair of adjacent integers in the list are 3 minus 1, 9 minus 3, 9 minus 4, because we got to make it positive, 11 minus 4, so we get 2, 6, 5, and 7 are the positive differences. In this example, the smallest positive difference between any two adjacent integers in the list is 2. It's the smallest right here with 3, 1. Okay. So it's a three-part question. A, arrange the integers 1, 2, 3, 4, 5 so that the smallest positive difference between any two adjacent integers is 2. So this shouldn't be too hard, just getting us introduced to the idea of positive differences and having a smallest positive difference in a list. So to answer A, it would suffice to give an arrangement of those 5 integers and then show that the positive difference really is 2, the smallest positive difference, of course. Okay, so let's get to it. It shouldn't take that long. There's 120 possible ways to arrange 1, 2, 3, 4, 5, so it's relatively small, and we can probably make this up as we go along. So we want the smallest positive difference. So really all we need to do is avoid adjacent numbers. We could even make a note of that. So I have the smallest positive difference be equal to 2, right? Equal. So I'd have it be equal to 2. We must have no consecutive numbers be adjacent and have at least one difference of 2. So we could have something like 1, can't have 2 there, but 3, so that difference would be 2. And so then at least we've got a 2 in there. Can't have 2 or 4 here, so we've got to go 5. Can't have 4 next to it, so let's go 2 and 4. So we could say this suffices. You could even double check. 3 minus 1 is 2. 5 minus 3 is 2. So we got a lot of 2's here. 5 minus 2 is 3. And 4 minus 2 is 2. So I imagine we're going to continue on with this positive difference stuff. And I'm wondering if sort of a sum of the positive differences might be fixed or something like that. I don't quite know. Because you get 5 minus 3 and 3 minus 1, that would just be 5 minus 1. And then, I don't quite know. Maybe there isn't a positive difference thing. Or maybe, I don't know. I'm thinking too much. I'm not looking at the contest. So that would suffice for A. We've explained our reasoning as now we made a list, and we did show that the smallest positive difference is 2. Okay, so B. Suppose that the 20 integers, so now we're being asked for a bigger list, are arranged, so 1, 2, 3, 4, all the way up to 20, are arranged so that the smallest positive difference between any two integers is n. Okay, so now it's not necessarily 2. So it's a two-parter inside this three-parter. 1. Explain why n cannot be 11 or larger. And then find an arrangement with n equals 10. These together prove that the maximum possible value of n is 10, because we can get one that is 10 for the smallest positive difference, and we know we can't get 11, 12, 13, and so forth. Okay. What to do here? So I'm trying to think in my head. I'm going to move on and read what C says, just in case that helps give me some sort of direction. Suppose that the 27 integers, 1, 2, 3, all the way up to 27, are arranged so that the smallest positive difference between any two adjacent integers is n. Same sort of setup. What is the maximum possible value of n? Prove your answer is correct. So to do C, we'd have to find the maximum possible value, say it's 10 again, show that the maximum possible value can't be 11 or higher, and find an arrangement with 10. So C is just doing the same thing as B, but with 27 instead of 20. And that's really it. So here in B, they're telling us 10 is the answer we want. In C, we would have to figure out what that n is. So how does 10 relate to this 20 here? To these 20 integers? And why can't it be 11 or larger? So the first thing that pops into my mind is 10 is half of 20. Now you can't half 27, so we'll have to do a little more investigation. But 10 is half of 20, and so the smallest difference being 11, there really shouldn't be, I guess, a way to space the numbers out. So there should be some way to show that some numbers got to be placed next to a number that's at least 10. So if we start to think about this, suppose we wanted a difference, a positive difference being 19. You'd have to have 20 next to 1. That's the only way to do that. For 18, you can have 19 next to 1 or 20 next to 2, that sort of thing. And you keep going down. There's for 11, for a difference of 11, there's got to be sort of some number that can't be put in a pair like that, I think. What number to look at? I'm guessing it's got to be sort of a number in the middle, because then you couldn't get far enough away with 1 or 20. Those are sort of the extremes. They're the farthest you can get away from any number. And so they can't be 11 or larger. So let's split it right there. Maybe 10 or 11 will do. So consider 10 in the list. 10 is adjacent. Is adjacent the term they've been using? Yeah, adjacent integers. Okay. 10 is adjacent to at least, because he's in the list. He could be at the start or the end, but he's adjacent to at least one other number. So 1, 2, 3, 9, 11, 12, or 20. And I guess this would be I part. But observe that the largest such positive difference is less than 11. So for example, 10 minus 1 is 9. 10 minus 2 is 8. 10 minus 3 is 7. 10 minus 4 is 6. 10 minus 5, of course, 5. 10 minus 6 is 4. 10 minus 7, 3, 2, 1. And then we get to 11 minus 10 is 1. 12 minus 10 is 2. 3, 4, 5, 6, 7, 8, 19 minus 10 is 9, and we get 20 minus 10 is 10. So we'll just finish this list off here, and then we'll go back to our conclusion. So the point is, no matter where 10 is, he's got to be next to one of these numbers at least, but that would mean that we get a symmetric difference less than 11. So the smallest positive difference must be less than or equal to 10, because those are our only options. Maybe 10 and 8 are next to each other, and 2 is thus the smallest positive difference. Okay, but it can't be 11 because we need to be able to get 11 in this list. And I imagine this doesn't just work with 10, this would also work with 11. But the idea is that this is sort of halfway, he's in the middle, so 1 and 20 are I mean, there you go to. If you wanted something to be really far away from 3, you'd pick 20. But that's still, you can only get 17 away there. So that's part 1. Now we need to actually find one that's got 10 as the difference. But I think, now thinking ahead to C part, I think something like half 17, so something right between 1 and, not 17, 27. Halfway between 1 and 27, so that'd be 14. I think 14 might be our go-to guy, and so, he's at most 13 away from the two n's, so I think n equals 13 is the best you can do in terms of the highest, smallest positive difference in the list. Alright, but let's get back to it with part 2. It really suffices just to show that you can get 10 away. So that pesky number 10, what are we to do with him? Let's go with 20. And then, well, we need something that's at least 10 away from 20. So 19, 18, 17, none of those will work. 11 won't work, but 9 is the first one that works. That's a positive difference of 11 there. Now we need something that's at least 10 away from 9, so 19 should work. And I think we see a pattern here. 7, 17, 6, 16, 5, 15, 4, 14, 3, 13, 2, 12, and 1, 11. And we can check really quickly. You'd probably want to write this up a little bit more, but here's our positive differences. And you can see the smallest is 10. Difference 4 and 14, positive difference of 10. 4 and 3, positive difference of 11. 11, 10, 11, and then finally another 10. Okay, so that definitely shows that this, so we might say, this is a list with smallest positive difference equal to 10. So that does it for B part. We've shown you can't have more than 10 as your smallest positive difference, and then we've given an example where you can have exactly 10 as your smallest positive difference. So that means 10 is the biggest smallest positive difference we can have. A little weird wording, but we want sort of the maximum of all the minimums, that sort of thing. Okay. So C part, do the same sort of thing with 1 to 27. And I've already said I think for C part it'll be 14, or like n will be 13. So let's explain how we're going to go about doing this. So we claim n equals 13 is the largest possible smallest positive difference. So it's the largest possible x, where x is smallest positive difference. For people who are still getting upset by largest of the smallest difference. Okay. We will prove this, because they do ask for a proof, by, and then we'll use the exact same procedure we did in B part that they gave us. They gave us a template for how to do this. If you think n is 13, show you can't have 14 or higher. Then get an arrangement with that has smallest positive difference of 13. So we'll show n has to be less than 14. By explicitly stating a list with smallest positive difference equal to 13. That would do it. That will work. So, if you wanted to, although I don't think so, you might want to justify why 13, but you really don't need to. Okay? Some people get hung up on this, I find, when I'm reading written solutions, is you have to explain where your 13 came from. No, you don't. You have to explain where your magical formula that spits out the number came from. You don't have to explain how you thought of it. You do have to explain why it's correct, though. And sometimes the best way to explain why it's correct is to explain how you thought of it in the first place. But that's not the case this time. I am not going to write down a single detail as to why I think 13 is the answer. I have verbally explained it to you guys, because 14 is in the middle between 1 and 27. So the farthest we can get, any number can be away from 14 will be the 1 or 27, which are 13 away. But I'm not going to say that. I will use 14 in my example to show that you can't have a bigger n, but I'm not going to say that this was my motivation or anything. I don't need to do that. I just need to show that it works. I just need to show n is 13. This is how I'm going to do it. I just need to show that my magical formula works. I just need to show that these are the roots of the whatever. And you don't need to explain where you got those, as long as you can explain that they are correct. And so that can sometimes, I mean, with this one it wouldn't be too hard, but it can sometimes take a load off your back that you have to, some people think you have to explain how your mind works and would think of these things. No, you don't. Not at all. So we'll go back to the I part. So it's going to be almost the exact same thing as with the 10. Consider 14 in our list. It is adjacent to at least one other number. But, and I'm going to give a partial list here. A is 1, 2, 3, up to 27, 26, and so forth. 13 and 15 here. So I'm going to make a little chart, positive difference with 14. So 13, 12, 11, all the way down to 1, 1, 2, 12, and 13. There is no number A in our list, so that the positive difference of A and 14 is bigger than 13. So n can't be or higher, because it's got to be the smallest positive difference, but 14 with some other number would give you a smaller positive difference than 14 or 15 or whatever we think. So that tells me n has got to be less than 14. It might be easier to say n is less than or equal to 13. Either they're equivalent statements, but maybe I'll change it in what I have to prove. So the smallest positive difference has to be at most 13. Now let's show that it can be exactly 13. So that's the other half. Because otherwise, I mean, maybe the answer is n equals 12. And yeah, n has to be less than or equal to 13, but maybe the best you can do for some other reason is 12. We got to show that you can actually get 13. And I think the exact same way. We're going to start with 14, go up to 27, go down to 12, and bounce around that way. I think that'll do just fine. So, part 2. Consider the list arranged as follows. 14 up to 27, that's a positive difference of 13. We want that to be the smallest of the positive differences. Then we go down to 13, then up to 26, again a positive difference of 13 here. 12, 25, 11, 24, 10, 23, 9, 22, 8, 21, 7, 20, 6, 19, 5, 18, 4, 17, 3, 16, 2, 15. I'm not going to make it. 1. Oh, we're done. All right. And, you might say here I'm labeling the positive differences. Got positive difference of 26 and 12 is 14. 25 and 12 have a positive difference of 13. It just keeps alternating quite nicely. But we clearly have a smallest positive difference in this list of 13. So we've got a list whose smallest positive difference is n equals 13. Uh, 17 and 3, positive difference is 14. 13, 14, 13, and then finally another 14. Whose smallest positive difference is 13. Thus, by proving 1 and proving 2, we see n equals 13 is the largest, smallest positive difference. And I'm starting to think that in general, you sort of, so if you were going from, so if you had A plus 1, A plus 2, all the way up to B, I think the smallest positive difference that you could have would be A plus B divided by 2 and then round it down if necessary. And that would fit with the data we've seen, 1 to 20. 1 plus 20 is 21, divided by 2 is 10.5, round it down to 10. Here, 1 and 27, so 1 plus 27 is 28, divided by 2, round it down is, oh, no, it's, alright, new plan, B minus A divided by 2, and round up if necessary. So 20 minus 1, 19, 9.5, round up to 10. 27 minus 1, 26, divided by 2, 13. No rounding up necessary. And I think we could probably prove that, actually. Yeah, why not? I mean, the question is over, so if you want to skip ahead to question number 3, B3. But I'm going to just take a gander at this for a moment. So this would probably be a faster way to do both B and C, but so suppose we got these numbers here, and we go from an A up to a B. Now, in both B and C, we've been using A is equal to 1, but it doesn't really matter. We claim n equals B minus A over 2, rounded up. That's what the ceiling symbol is, rounded up, if necessary. is the largest, smallest positive difference. And so we can prove this the same sort of way. We'll have sort of two cases, I think. No, we won't need two cases. So you might say something like, consider b minus n, who's in our list. And then, what now? Let's say this a little bit better. I don't want to have to do two cases where the difference between A and B is even or odd, so I'm trying to avoid that. And this might be a little conceptually harder, but let's say so we've got this n here, so either b is equal to a plus 2n, or b is equal to a plus 2n plus 1. Does that track? No. 2n minus 1? Yeah, because of the ceiling function. So either the difference between A and B is even or odd, doesn't matter, we'll cover both of those cases. Okay, consider C being equal to A plus n minus 1. Is that the one I want? So I want something that's the same as 10 or 14. So we'll go with b minus a over 2. Right? No. No, we'll do a plus n. A plus n. Okay. Notice that in any list, C is adjacent to at least one other number. The positive difference of C with that other number is at most either C minus A, which is equal to n, or B minus C, which is B minus A plus n, which is B minus A minus n. But that's going to have to be less than or equal to B minus A minus B minus A over 2, which is B minus A over 2, which is less than or equal to n. So both of these differences must be at least n, right? Because n is a little more than half. So it has to be at least that, which is So either a minus b is even, or in which case these two numbers are both equal and they're both equal to n, or the difference is odd, in which case this is actually less than n. So it's less than or equal to n. Okay, so that is true. I'm not going to dwell on talking more about that. So the smallest positive difference must be at least n, because that's the best you could get for that difference. The difference with c and any other number is at best n, because it's made by the extremes, either b and n or a and n. So we're good there. All right, so now for part 2. So to show n is the largest, smallest positive difference, we just need to find a list with n as the smallest positive difference. Okay, and we can make one the exact same way we did before. So we start with our interesting number, a plus n, and then I would go, actually I'm going to reverse it so it's a little more obvious what's happening. Go down to a plus n plus 1, and then we'll go down to a plus 1, a plus n plus 2, down to a plus 2, and it'll just keep going. And then eventually you will get b minus 1, and then you'll have b, that's the big one, and then we go down by n. So b minus n plus minus 1. And that will still be less than n. So we're still fine. And then we would go up to b, and then we either go down to b minus n, or no term at all, if b minus n is equal to a plus n. Okay, so this guy here, it might end at b or it might end at b minus n, depending on whether the difference between a and b is even or odd. Okay, and we can check that out on our own if we want to. But constructing this sequence as we have, we've got difference of n, n plus 1. Difference of n, n plus 1. Difference of n, the next one would be n plus 1. And every time we go up to the high one, it'll be n plus 1. Then we go down by n, and then we go up by n plus 1. And this would be, if it needs to be, would be a positive difference of n. And that finishes everything off. So thanks if you stuck around for that. You didn't really need to, but that proves b and c together in a single stroke. Although if you were going to use something like this to prove it, you might want to explain it a little bit better than I did. But there it is. That's our general result. Okay, so a nice little extra bit that we did there, and we'll flip the page in anticipation of our next question, and that will actually be B3, and that'll finish off the whole contest. Looks like it's going to be about something called Murray numbers. We'll take a look at that next time. So as I said, thanks for watching. I'll see you next time.